Hello and welcome to Computing Fundamentals 2. There are many useful ways to represent graphs, as we will see in this video. Working with the graphs, it's helpful to be able to choose its most convenient representation. In this video, we will show how to represent the graphs using adjacency lists, adjacency matrices, and incidence matrices. One way to represent a graph without multiple edges is to list all the edges of this graph. Another way to represent a graph with no multiple edges is to use adjacency list, which specify the vertices that are adjacent to each vertex of the graph. Let us take a look to the graph G shown in figure 1. To represent the graph G using adjacency list, we need to draw a table that lists all the vertices of a graph G. And in the second column, we will specify the vertices that are adjacent to each vertex. For example, the vertices B, C, E are adjacent to vertex A. Vertex A is adjacent to vertex B, as you can see from table 1. In figure 2, we can see a directed graph that we need to represent it using an adjacency list. First, we put down the initial vertex, for example A, and its terminal vertices. We have B, C, D, and E, which are connected to A, so that we call them terminal vertices. Vertex B has a loop, so B and D are terminal vertices of B. But vertex D has no terminal vertices, as all edges are going into D, not in the opposite direction. The adjacency list for directed graph is shown in table 2. Carrying out graph algorithms using the representation of graphs by list of edges or by the adjacency list can be difficult to handle if there are many edges in the graph. To simplify computation time, graphs can be represented using matrices. Two types of matrices commonly used to represent graphs will be presented here. One is based on the adjacency of vertices, and it is called the adjacency matrix. And the other is based on the incidency of vertices, and it's called incidency matrix. In next slides, we are going to describe both of them in details. We are going to represent the graphs using adjacency matrices. Let us take a look at a graph G in figure 3. In adjacency matrix, we think of rows as well as columns of the matrix to be labeled by the vertices. So we have A, B, C, and D vertices as rows, and we have A, B, C, and D as columns, as you can see in figure 4. So let us call our adjacency matrix A. And by definition of the adjacency matrix, we know that an entry in row I, column A, will be equal to either 1 or 0. It will be equal to 1 if the edge I and J is actually an edge, and 0 otherwise. So let us take an example. So if you look at vertex A and then you ask, is vertex A is adjacent to A? The answer is no, because that will be a loop, so you put 0 there. Is vertex A is adjacent to vertex B? The answer is yes, so we put 1 in that row. Is vertex B is adjacent to vertex A? The answer also yes, so we put 1. Is vertex C adjacent to vertex A? So the answer also yes, so we put 1. And we will do the same for the rest of the vertices. The complete adjacency matrix for the simple graph G is shown in figure 5. So if you notice that if we have vertex B, and vertex B is adjacent to A, so we put 1. Vertex B is not adjacent to D, so we put 0. Vertex B is adjacent to C, so we put 1. And vertex B is not adjacent to D, so we put 0. Let us take another example about representing a graph using adjacency matrix. This time we are giving the adjacency matrix shown in figure 6. And now we need to draw the graph based on it. Once we have 1 in the entry of row I and column J, we draw an edge between the vertices. If we have 0, then there is no edge between them. As a result, the graph H is shown in figure 7, which representing the adjacency matrix shown previously in figure 6. Adjacency matrices can also be used to represent undirected graphs with loops and with multiple edges. A loop at the vertex V of I is represented by 1 at the entry I and I of the adjacency matrix. When multiple edges connecting the same pair of vertices like V of I and V of J, or we have multiple loops at the same vertex, The entry of this matrix equals the number of edges that are associated to V of I and V of j. All undirected graphs, including multigraphs and pseudographs, have symmetric adjacency matrices. So let us take an example of pseudographs where we have multiple edges and loops. This graph is shown in figure 8. Consider that graph P has loops and multiple edges between its vertices. This means that an entry between vertex A and B is equal to 3, because we have 3 different edges between A and B. When we have loop, as you can see at vertex C, the entry associated between vertex C and C is equal to 1. Finally, we need to remember that rows and columns in adjacency matrix represent vertices of the graph. The row sum equals the degree of vertex the row represents. For example, if we ask what is the degree of B, we are going to find it's equal to 5. Look back into graph shown in figure 8, you will find that degree of B is indeed equals to 5. Another common way to represent a graph is to use incidency matrix. But first, we need to understand what we mean by incidency matrix. So the incidency matrix is usually denoted by M instead of A. There is only one key difference. We still are going to be labeling our rows by vertices, but now what we need to do is to label the columns by edges. Figure 10 is showing an example of incidency matrix with 5 vertices and 8 edges. So let us take an example of incidency matrix. As you can see in figure 11, there is undirected graph that we need to represent using incidency matrix. To represent this graph, we need to draw a matrix M with 5 rows as the vertices V1, V2, V3, V4, and V5. In the graph, we have 6 edges which represent the columns of the matrix M. And by definition of adjacency matrix, we know that an entry in row I, column j, will be equal to either 1 or 0. It will be equal to 1 if the vertex I belongs to the edge E of j, and 0 otherwise. We can see vertex 1 has several edges that lays on, so it has E2 and E1, so we will put down 1 below E1 and E2 in the matrix. For vertex V2, we have the degree E3, E4, E6, which are connected to it. So we put 1s in the associated cell. The complete incidency matrix for this graph is shown in figure 12. Now when you look at the row sum of the incidency matrix M, you are going to get the degree of the vertex associated in the row. When you look at the row sum of V2, you're still going to get 3. That's telling there is the total of 3 edges that V2 is incident with. When you look at the columns, you will find that the number of 1s is always 2. So if you look at E3, you will find there is 2 entry. If you look back at E2 in the graph, you will find it does indeed has 2 ends, and this is basically the actual definition of an edge that has 2 ends. In this video, we have covered the following topic. We discuss adjacency list, adjacency matrices, and incidency matrices. Next video, we are going to discuss graph isomorphism. So thank you for watching this video and see you in the next one.